All right, in this video we're going to compute a definite integral using the limit definition. Just to recall what that is, it's the limit of the Riemann sums as we use more and more subintervals. For the Riemann sums is the sum of the function value evaluated at the point in the case subinterval times the subinterval width added together, and we're taking the limit as n approaches infinity and the maximum width of the width of the largest subinterval is approaching 0. Now, for the next couple examples we're going to look at, we're going to use what we call a regular partition, and doing so, as we showed in the last recording, the subinterval width is going to be constant. It's going to be the same. All right. So for this recording and for the next couple, delta x of k is just going to be delta x. All right. And that's going to be the width of your subinterval, length of subinterval divided by n. We're going to break it up into n subintervals of equal width. All right. So just keep that in mind. And we saw this in the last recording, but if we're using a regular partition, breaking the interval into n subintervals of equal width, we have the following for the right endpoints, where we have the right endpoints given by this formula, the left endpoints given by this expression, the midpoints given by this expression. So that was a little bit of work to express that out. And notice we know what delta x is also. It's going to be b minus a over length of your subinterval divided by n. All right, so we're going to be able to then take that expression and substitute it in for delta x in one of these scenarios, whether we're using right endpoints or left endpoints or midpoints, in for delta x. And then we're going to have a number to plug into the function f and evaluate, and then multiply that result by delta x and add the results together. All right, for us to be able to use the limit definition, we have to, we're not going to often do this by hand, but we are going to see a few examples where we're going to do it by hand using the limit definition. And then we're going to learn about the fundamental thermocalculus, which is going to make it a lot easier for us. But in order for us to do these problems or evaluate these definite integrals using the limit definition, we have to know some important close summation formulas. If you add up 1 plus 1 plus 1 n times, you get n. Not too surprising there, but that's just a small one that's not covered in most books. If you add up the first n integers, it turns out that adding those values together comes out to exactly equal this expression right here, n times n plus 1 divided by 2. A little bit surprising there. All right, if you add the sum of the first n integers squared, 1 squared plus 2 squared plus 3 squared up to whatever value we're talking about, turns out that that adds up to a nice formula also. N times n plus 1 times n 2n plus 1 all divided by 6. If you add up the sum of the first n integers cubed, 1 cubed plus 2 cubed plus 4 cubed, or plus 3 cubed plus 4 cubed, etc., up to however many you want to add together. I want to shift that. It's going to move my inking there. Then we get another, what I call closed form expression, n squared times n plus 1 squared divided by 4, which notice that happens to be the square of the second formula listed here. So again, we are going to be using these. I'm not going to prove them in this video. We're going to take those for assumed facts. All right, so let's get after the example. So now what we're going to do is evaluate the following definite integral. All right, we're going to use a regular partition and we're going to use right endpoints. All right, now notice we're given the lower endpoint is 0, so that's a. The upper endpoint or limit of integration is b, so b is 5. All right, so again, a is 0, b is 5. The width of our subintervals is going to be b minus a, so that's going to be 5 minus 0 divided by n. So delta x is 5n. Okay, just make a note of that here. All right, now we want to use right endpoints. As we said before, that's going to be a plus k times delta x. That's something we derived in the last recording. Now let's actually plug in what these values are, and then we're going to evaluate that into our function. All right, one thing I want to stress here, the function is 2x plus 1, so f of x for this problem is going to be 2 times the input plus 1. All right. Now, what is A? A is 0, so we're going to have 0 plus k is a generic or dummy variable times delta x, which we know is 5 over n. So this special number x of k star that we're going to plug in is just going to be simply 5k over n. All right, now let's write out our Riemann sum. All right, so what we're going to do is we're going to think about n being temporarily fixed. So think about n as a fixed value. It's not changing yet, and then we're going to drive that limit to infinity. And then what we need to write out is our Riemann sum. So we want to do the sum from, we're not doing the limit yet, k equals 1 to n of f of x sub k star times delta x. And now we're just going to simply plug in and use the definition of the function 2x plus 1 and plug in 5k over n into that function. And then we're going to plug in delta x, which is 5 over n, in for delta x there, and then see what simplifies. Okay, so keeping going here, we got the summation. Again, it's a little bit tedious to write this up. We're going to have to do that every time. And then we're going to do f of 5k over n times 5 over n. All right, now I'm going to evaluate the function next. So we're going to plug in 5k over n into our function, which in this case is 2x plus 1. So that's 2 times the input plus 1. And then that's still multiplied by that 5 over n there. And again, what we're inputting in here is 5k over n. It says it's going to make that simply 10k over n. All right, now one thing we can do to simplify our life a little bit here is we're summing this up from k equals 1 to n. All right, this 5 over n, again, since n is fixed, that's a fixed factor. We can take that factor outside of the summation sign. So let's make sure we do that in the next step here. So we're going to pull out, we're going to pull out 5 over n, and then that's going to be times the summation from, again, k equals 1 to n of, now just multiply this stuff out, we're going to get 10 k over n plus 1. And then we're just going to do a little bit of rearrangement, and then eventually we'll be applying those summation facts we had up above. Now, looking at this, again, we're just going to do a little, moving my inking on me here. So we're just going to do a little bit of rewrite here. To, again, we still have the 5 over n times, and then I'm going to put a big parentheses there. Then we've got our summation inside of there again, k equals 1 to n. I just want to rewrite this as 10 over n times k, and then it's still plus 1. And the idea behind that is we're going to split this now into two summations. All right, we're going to sum up, because this is really all being summed from k equals 1 to n. I messed that up a little bit on me here. Let me just fix that. All right, and we're going to split this up into two sums, and then we're going to apply the summation facts we discussed before. So we still got continuing here, 5 over n times, now I'm going to use this big parentheses, we're going to have two summations. All right, and then one more step before we can apply the summation formulas, we can for the second sum that's in here, but not for the first one yet. So we're going to, again, take use of the fact that n is a fixed constant, therefore 10 over n is currently a fixed constant, so we can take this out of this first summation and put that in the front, because that's a common factor to each one of those terms when we go to add that up. And so we get next that we have, again, still 5 over n out front. Then we're going to have 10 over n times the sum of the first n integers. We know a formula for that, plus the sum from k equals 1 to n of the constant function 1, all right, which is going to just add up n1s, and that's going to turn into n. All right, so now what we're going to do, we're not taking any limit yet, we're just going to substitute in what we know. Okay, so we know from our showing up above, this is equal to n. The sum of the first n integers. And what this is saying is you're adding up from k equals 1 to n, k. So it's going to be plugging in 1, then plugging in 2, then plugging in 3, plugging in 4, adding them all together. That we know multiplies out to, or comes out to, n times n plus 1 divided by 2. All right, so now we can just say that those are equal. They're legitimately just equal to those. So this is going to equal 5 over n times 10 over n times n plus 1 divided by 2. No summation sign anymore. The summation sign's gone because we've said that they're exactly equal. Plus, and this is just going to be n here. All right, we'll do a little simplification, and then we're going to eventually now take the limit. So what can we simplify? Well, let's see here. 2 goes into 10 5 times. We cancel this factor of n with this factor of n. Then we're going to distribute the 5 over n in through the parentheses. That's going to give us 5 times n plus 1 divided by n plus 5 over n times n. These n's will cancel out. All right, I'm just going to rewrite this one more time, and then we're going to drive the limit to infinity. So we're going to get 5, and I'm just going to rewrite this as 5 Okay, I caught a mistake in my maybe you recognized it when I multiplied the 5 over n through here. We're going to have 5 times 5, so this right here should not have been 5. That should have been 25. All right, so I'm just going to fix that mistake there. So this should have been 25. I missed the 5 times 5. Everything else is correct. All right, and then we're going to rewrite this. So again, fixing this over here, we're going to have 25 times, I'm just going to combine these factors, n plus 1 divided by n, and then plus 5. All right, now, eventually what we want to say is, all right, what happens as n approaches infinity, as we use more and more and more and more subintervals? All right, so what happens to those quantities as n approaches infinity? Well, this one's staying fixed. This is approaching 5. This thing right here in the parentheses is approaching 1, so this whole quantity here is approaching 25 times 1, which is 25. All right, so the whole deal is going to approach 30 as n approaches infinity. All right, so let's just finalize what we had done there. All right, and I'm just going to come back to that expression. I'm going to put it back in. All right, so again, using the limit definition, we had the integral from 0 to 5 of the function 2x plus 1 dx. That is going to equal, since we're using a regular partition, it's just the limit. Sorry, OneNote crashed on me. So again, that's going to be the limit as n goes to infinity of our Riemann sum. Now we wrote out our Riemann sum and did all of the work, and that simplified down to this expression that we had here, 25 times n plus 1 over n plus 5. All right, so that definite integral is equal to that limit as n approaches infinity, and we can confidently say that that is going to therefore equal 30. And there's a way to view this geometrically also, because we have a linear function here, and so if we think about graphing this, line 2x plus 1, that's familiar to us over the interval from 0 to 5. We're talking about getting the area under the curve. Well, that's a trapezoid, or a trapezoid turned sideways. The area of a trapezoid is 1/2 times the sum of the bases times the heights. So we have one of the bases is 1, one of the bases is 11, and the height is 5, so we'd have 1 plus 11 times 5. Well, that'll give us 12 times 1/2, which is 6 times 5, which will give us 30. That's just a check geometrically that the area under the curve is matching up what we got using the limit definition of the definite integral. Clearly much more tedious and much harder to use.